And so now, Michael, are you going to run the show for the discussion?
Yeah, so we have almost an hour for discussion, and I'm hoping those of you in the room, especially Jonathan, can kind of help organize this. So the idea is to first have a discussion about what you want to discuss. So this is the sort of unconference idea, rather than us having some kind of agenda. We actually want to know from you, the participants, what you want to discuss. We've had kind of a wide variety of interesting papers today. There are also other topics that we could talk about that maybe didn't have any papers represented today, and those are also good to talk about too. So maybe Jonathan, since you're in the room, if you could help sort of facilitate a 5-minute planning session where we kind of solicit ideas for what we want to discuss and how we want to discuss it, and then we'll do it.
Yeah, absolutely. Can you hear me? Yes. Okay.
Yep.
So, yeah, I have. Sorry, I'm making everyone busy, but we have. Maybe I'll point this towards the room. Yeah. Okay. So, in line with Michael's idea, we could. Maybe we can organize it around topics or questions people would like to discuss. Maybe some of them are questions that we were starting to talk about in previous papers. And if you're a paper author and you want to propose one that maybe relates to your work, but maybe relates to some of the others, please go ahead and mention that. And I will write them down in some form. I'm trying to see if I have a whiteboard marker, and I don't see a whiteboard marker.
I have one.
Oh, you have one? Okay, awesome. Okay, so I can write down something on a whiteboard, or I could put it in the chat. That might be better because then everyone can see it, including Michael and Alan and the other remote participants.
I can listen and copy things into this chat if you want to do it that way.
Yeah. Okay. So ideas. Yes.
I guess it's kind of broad, but like the role of AI and NLP. I think there was a co-pilot paper, and then there's lots of teaching stuff.
The role of AI and NLP. Okay.
Yeah, maybe it's also good to have it on the board as well as in the chat.
Yeah. Okay. Good. Good. Well, let's see. We had a couple others. Well, I'm writing this down. Michael.
I think that a lot of the power of type systems and automated reasoning is in the specifications. Whether you use your specifications for property-based testing or for automated proof with Daphne or semi-automated proof with Coq, you have to have a specification, and it has to be a good specification. Types, that's another kind of specification. It seems like the advance of any of these techniques requires users to be able to write specifications and believe that they're true. So how can we help people learn to write better specifications?
I mean, the thing I've been thinking about is that then is about tests and specifications as well, maybe specifications and tests.
Specifications and tests. Yes.
I was gonna say that we could talk about how to influence community norms. So I think during the question of using proof assistance, we talked a lot about, or at least Cyrus earlier brought that like part of the reason people might not be using proof assistance because the community expects certain things about like the guarantees that it provides, and it's really hard to change what people think is appropriate, right?
How would you go on?
Yeah, absolutely. That'd be great.
I didn't quite get that one.
Community norms and expectations, and how that influences the way people
And how to influence them, right? Like, if you want to.
How do we influence those community norms? Yeah, sorry, you have the microphone there now. How they influence us and how we influence them.
Okay, thanks.
Okay, yeah, that's I like this. So one thing that I have been thinking about a lot recently. It connects some to the paper with Haman's, but also some of my other work is the role of partiality, right? I think one of the things that's, and this connects with specifications because we often write partial specifications before we write full specifications, but it also relates to things like testing because you may not be able to prove a partial specification, but you might be able to test against it.
Or a test is a very partial specification.
What?
A test is a very partial specification.
Yes, a test alone is a very partial specification, right? But if you have a partial, more of a traditional specification, but it's partial, you can also test, you can generate tests for it and things. So, yeah, good. That goes both ways. So including partial. Okay, well that's a pretty good list. Any others? Alan, yes.
Yeah, so one thing that I'm quite interested in is I know absolutely nothing about computer science education, apart from having done it, but the actual CSE literature I am mostly very vague about. But it seems like there's an interesting interaction between the way that beginners build notional machines for thinking about how programs execute and the feedback they're being given by the type system. So the type system is presumably like intended to ahead of time warn users about pitfalls that their programs might fall into. And how do we ensure that the machinery that the user is then internalizing from that feedback actually lines up with the notional machine that hopefully we're trying to get the users to learn?
Yeah. Education, notional machines, error messages, etc. Okay, good. Yes, Haman.
I guess just a small add-on to that previous comment.
Yeah.
Something that might be interesting to talk about is how far we can push existing, like research on formal, like existing formal methods theory with just like better error messages and better like things that are targeted at just like onboarding people and making these existing things really usable. So
Right.
Sort of like the Rust approach.
Yeah. So good.
I didn't quite catch that one either.
How far can we push these things?
You got a microphone that one.
Yeah, that's right. We okay. Any other stat of the list, or should we go with that?
We can always come back
We
to
only have
add more
15 minutes.
Yeah, we can. Let's start. Let's go with it. Yes. Okay.
I guess Michael was saying he missed the last.
The last one was extending the idea of notional machines and error messages. How far can we push tools to make them more usable?
to like help with onboarding.
To help with onboarding, right? How can usability? How much difference can we make alone kind of with usability improvements to get these tools more widely adopted and used? Okay, so let's see. Maybe we should also bring all the other remote participants into the virtual room. So I'm thinking of looks like Alcides and Farhan. Yeah, let's look at some of these. So someone want to take a crack at diving into one of these topics?
I actually have a way to connect a few of them.
Great.
So one of the things that I've been imagining in the last few months with the rise of GPT-3 and Copilot, and a couple of people have tried to do,
is to use those kind of tools to generate proofs for COC or other systems. Assume that this is going to work. Assume that in 15 years from now, you just have to write good proof statements, and maybe you have to write a bunch of intermediate lemmas to guide the machine, but that's it. You can get your specifications, on your code, and you can get those be the proof, and the hard part being automatically generated. I'm giving this like a 40% chance of happening. So how this will change our reality? In particular, since those kind of proofs are now going to be away of the eyes and the mind of the people, the soundness of those verifiers is going to be dramatically important. And I mean, if there is a way to break HATRA, even by leveraging on a random bug instead of a fundamental problem, the artificial intelligence is going to find it and just say, yes, your proposition is correct, And so, yeah, what do we think about this?
Because it seems to me, if we're talking about mass adoption, most software has no specifications, or the specifications are loose or partial. And so I guess I wonder how risky the situation really is.
I think the idea was that if this capability comes around and people start using its power and write these specifications, is it likely to give a false sense of security because maybe the IO will find the bug? I guess my opinion is, well, there was a paper that was published by the ComStart team, I think it was in the last year, where they reflected on the last 10 years of ComStart of having this verified compiler, right? So they did all the proofs and COF. And they said, there's going to be bugs in the compiler. What were the bugs and where did they come from? So some of the bugs were in the specification. You get the specification wrong, then it's correct according to your specification, but it's still wrong. So they had to fix the spec. This had to do with their back-end machine code generators. They got some of the specs wrong for the underlying machines. In some cases, they had bugs in parts that weren't verified yet. So in the parser and in the assembler, I guess, were some sources of bugs. They never found a bug in the verifier. There was never a bug in COF itself. It was always bugs in the surrounding infrastructure. So my suspicion is maybe there'll be a bug in these things, but I think the probability is low compared to if there's going to be bugs in everything else. That is, this will raise the game, and software will be a whole lot more correct than it used to be, and there may still be some bugs in it, and it will start finding those bugs instead.
So I just ran a workshop called Unsound yesterday, and while if you do proof by hand, you naturally tend to avoid those sources of unsoundness, at least in quite a few cases. If a machine just chunk through all the possible proofs with some heuristic, they are basically going to be a very good model checker if they desperately try to prove false, independently of the logic, many of those ways to break those tools does look unnatural, like, oh yes, I have a list, I have a predicate. What if I have a list of predicates? And my predicates, take the predicate and sort of emulate the omega with it. If you do it by hand, you may recognize that you are doing that. But this is one of the first things that an artificial intelligence is going to try. That's what they are doing. That's what they're good at. So if there are bugs in the verifier, those are the first thing that this is going to find and leverage.
I mean, I think this is certainly true for sort of the traditional style of proof search, where you are just hammering at it away. But I think my understanding of the sort of newer, NLP-oriented approaches is that they are essentially generating proofs that try to look like human-written proofs. So I wonder if somehow that's working against this sense in some way. No?
No, I have done some study on AI safety, and I have tried those GPT-3 and stuff a lot, and I use them to write my articles. Mm-hmm. Hey, Paul and Marco are talking about, brainstorming about an article. Those paragraphs looks unclear. Can you help me to make it more clear? Sure, for example, in line 3, you could, and then I can take it up, and write the better articles. But in the same way, tools like AlphaFold and so on are instead very, very good at not necessarily emulating a person, but to find those kind of loops and issues. So it's a mix of the two.
Okay. Then I want to go to Alcides, who made a comment in the chat, but yeah, go ahead.
So briefly, I think this goes back to the last discussion we had before the break, where we're talking about these verifiers like HATRA and COC have this very small kernel. And kind of the idea is of that is we can do whatever we want in our proof search as long as we can satisfy the small kernel and believe that that's very reasonably correct. Then we can't really like exploit it per se. And I think that might help with the AI issue in that if we have this very small kernel that we can't exploit, then the AI can be as opaque as we like, as long as the proof verifier accepts it, it's sound. Kind of related to that also is, this doesn't completely sidestep the issue you're talking about, but in models like GPT and such, if they're not like hooked up to the verifier, like if we're not repeatedly asking them generate a proof until it gets one, if we just ask it once and use that as a baseline, it doesn't really have a feedback loop to really try and find an exploit.
Give it a few years. There
Yeah,
are maybe approaches.
It's kind of a soft maybe, but maybe that would contribute to not finding an exploit. Just a thought.
So I saw Alcides made a comment online. Do you want to unmute Alcides and join the discussion?
Yeah, so this was a comment to something that Michael said, I think, minutes ago, regarding the incremental nature of specifications. So whether we wanted to go for partial or complete. And my point is that I don't believe there are complete specifications in the real world. So there are many vectors you can.
All the remote speakers are looking blurry.
Sorry, did this help? Not really.
Actually, that helps. Yes. Can you say that again from the beginning?
Yeah. So I was answering Michael's comment on having a partial versus complete specification, and my belief is that in the real world we don't have a complete specification because, well, engineers might not be aware of all the constraints being functional or non-functional properties. So I think it will always be incremental in the nature, right? And right now, I don't think most tools are designed that way. And I agree in the comment that property-based testing goes in that way, in which you can write a few properties and go that direction. But I think even more formal specification systems could be done that way, going step by step. So I think the way users interact with these systems in incremental ways, I think that could be more explored. And for instance, gradual typing is just one of such examples. There are more.
I wonder, I mean, so Jonathan, I know you and Jenna have done all this work on gradual verification. Is there an approach toward gradual verification where on the non-verification end of the spectrum is property-based testing? You know, so you write down a bunch of properties and.
Sorry, can you?
Oh yeah.
A little shaky. We got the first part of both of Alcides' comments and the first part of yours, Michael.
Oh, I was thinking about your work on gradual verification, and you know, what if property-based testing were one end of the spectrum? You know, so you write down your specifications and some of the properties you can prove, you know, formally, and others you have a property-based testing mechanism to try to verify or test, maybe I should say.
Yeah, that makes a lot of sense. I think there's so maybe part of the the issue of partial specifications is what can you do with specifications that are not necessarily inductive in the sense of a proof assistant or like Daphne or Coq or something. So we've been exploring. Michael mentions our work on gradual verification, where we've been exploring a hybridization between runtime verification and static verification. But I think things like property-based testing are another great way to work with kind of non-inductive specifications and make progress toward confidence and correctness or finding bugs, etc.
I mean, the other way you can be partial is by not specifying everything that matters, right? We never maybe really specify everything that matters. So there's always the notion where you can specify just the two things you care about most first.
Right.
But it's always hard to find the specifications.
How about the idea that the surface area for the stuff that we can even specify precisely is shrinking, right? We've talked about these large language models a few times today already. Who is ever going to be able to write down a spec for what those models should be doing? And therefore the role of humans to curate and to have much sort of looser specifications for what we're developing may actually increase. I don't know. I sort of worry that the surface area is shrinking too.
Is it shrinking, or we are just discovering that it was always small to begin with?
I think if any automated approach, whether it's automated testing or automated verification, is going to add value, you need some sort of specification. Now, type systems, type store specification, they're an extremely partial specification. This is an integer, that's it. This is a string, that's it. But it's telling you something, and even people who program in JavaScript really want that specification, and now they program in TypeScript. Types somehow are hitting a sweet spot in getting people to write specifications. Upping your game a level to properties with for alls and more interesting stuff for property-based testing, then it gets a little harder. For information flow control, that's another kind of specification, and I think your work and many other pieces of work are interested in, well, how do we specify the property that we want in a way that is, I think another key part is that it's independent of the code that you're specifying it about. If it's just completely aligned and isomorphic with it, you're not thinking about it two different ways, and you're unlikely to catch the inconsistency between the two. Whereas a type versus an algorithm that computes over the type, those are very different thought processes. It's the data versus the code. I think all of these things that are important, but all of them, yes, I guess this is just reiterating that specifications I think are super important. And somehow, just as an educator, as a researcher, getting more, as now an engineer at a company, getting more and more people to think in these two ways about their system, the code that they implement and what they want it to do, whether it's partial or complete, so that they can cross-check one another. I think that would be amazing. And then using AI and testing and automated reasoning to cross-check these things, this could scale up pretty very exciting.
I think that's a really interesting comment about the sort of abstraction maintained between the specifications and the code you're specifying. And I think, I've used some dependent type systems like very briefly, and that's sort of something I noticed when you try to write down like very powerful type signatures that eventually at some point you end up putting a lot of the implementation of the function in the type, and it's just like, okay, what am I specifying anymore? I'm just statically executing the function like it's. And I guess it might be interesting to explore, falling back to the earlier discussion on sort of proof search and how that interacts with the soundness of our current provers. Like, okay, naturally, once you make your logic powerful enough, it's not self-formalizable, but like, first order logic is complete. And it might be interesting to explore like proof search on provers that implement like a restricted and easier to validate like subset of some interesting logic. Like separation logic or like higher order forms of it, right? It might be interesting to explore, like, okay, I have some restrictions on my logic, and that makes it maybe that makes it complete. Maybe that makes it easier to verify that there are satisfies in it. Yeah.
So one thing I liked about your comment, Mike, is that I think you're getting at the kind of the engineering wins for specifications, right? And it's been interesting to see this over time. I feel like maybe with Java 25 years ago, kind of sound type systems broke into the mainstream and became moved from kind of an academic curiosity to something that everyone was using. And now, so I think something similar is happening with Rust. We're seeing fancier types, in fact, of ownership in this case, breaking into the mainstream. I kind of I have two minds of this because I've been working on ownership types for 20 years. But I was working on kind of every application of ownership types except memory management.
That's the boring one.
So, well, I don't know that it's boring, but I was interested in more software engineering kinds of things, and memory safety is the killer app. Well, now that we have it in Rust, we can use other things. We can use it for other things like maybe information flow. So that's great. But where are the other places where we can really kind of find? I don't know what made it break through, but something about people really care about the memory safety and some combination of that and the ownership type systems moving close enough to kind of reality that it became feasible to kind of put them everywhere. So you had something in that work.
Yeah, so I think the comment about Rust again is interesting. This will be quick. So I think one of the other really interesting things you can do with Rust is it actually lets you do type state very naturally. So they have a whole section on embedded development with Rust where you're managing the state of an external device, and you can basically encode using ownership types like, okay, my external data that I'm communicating with in the real world is in this state, and once I transition to this other state, the object gets consumed, and I get back this other thing by move, and so on and so forth. And yeah, Rust. I didn't talk about it during our presentation, but Rust also has, as far as PL work goes, this really interesting property where it knows for all pointers in the program exactly where that pointer points modular branching information. And that's something that a lot of analyses really, really want to have. Because doing this on Java is just terrible. It's really hard to make it precise. And Rust can just do it. It already does it. And I'm sort of interested to see where that how it gets taken advantage of.
Surprised we don't have 1,000 PLDA papers on this already.
Yeah. Funny enough, Will Griffin's work on PLDI last summer was actually on this.
Inspired our work.
Yeah.
So to me, one of the big issues with trying to verify software is that what you're really doing is not verifying the software, you're just rewriting the software into another language that is different, and some people believe better, more formal, and then you prove that the two systems are somehow compatible. One thing that I've tried to do to avoid this duplication was to have a system where you have actually unobservable object invariants that are conceptually checked at runtime, but thanks to some ownership and things, you can know when exactly you have to recheck it, so that whenever you take a person, you know statically that the invariant of the person that is wrote in the language itself is holding. And then if your function returns a data type that has an invariant that is more sophisticated and offers more feature, you know that sort of becomes the post condition. But you are propagating this around, you don't really have to repeat, to re-specify every function in both the programming language and the formal language. You just have to take a few crucial data types and give them a very good invariant, and that will really help you to specify the behavior of the code without duplicating the code.
Pass it down to Gabriel next.
After
you.
Oh yeah,
Oh,
sorry,
yeah,
I see a hand up and I passed the mic. I don't want to step on anyone.
I'm just going to be quick because I think it connects with what you just said. It was mentioned that there's this challenge potentially of specifying these language models that are very complex in examples. I think another concern of kinds of systems that are, as far as I know, difficult to specify are those that interact a lot with the real world in some way and with humans in some way. So there's interface for managing a warehouse and the way the system handles the warehouse. All of these things end up encoded in essentially by a copy of, or if you want to specify this, you will need to make a copy of the entire program because the interactions that these programs have with the world and with the user are informally specified in the program themselves. Like the business logic, I suppose they would call it, is massive. And having another copy is not clear if it adds much value because it ends up being another kind of unspecified, or rather specified, but also the equivalence is not very, very useful. So I guess it's more of a concern than any thought on how one should go about it. Is like, how do we apply formal methods in contexts where the specification surface is huge?
That's a better specification.
That's sort of what I was.
Seriously, we never talk about that. Why is formal logic the best specification?
If we want to get.
Yeah.
Yeah, no, I mean, that's kind of similar to the things that we mentioned before, like executable code is a specification, right? And it turns out that in many scenarios, that's all the specification you need, right? Like in the case of fluttering a website, like the function is 4 pixels to the left and not 7 pixels to the right. It's like, it's pretty much arbitrary. Like there's not like a higher level specification. You could probably have like properties of like maybe there shouldn't be 2 items on each other, right? But I don't know, I think that's probably something that we should consider more about. And I think it even relates to like the success of Rust was, the killer application was not because, this is like the most elegant or the best way or the nicest specification. It was just, this is very evidently something that people have been struggling with for like 20 years or something. Memory safety issues are like the #1 or top 5, 5 of the top 10 issues in like security vulnerabilities. And so like, I think that was like the main driver. And so I think maybe we should spend more time thinking about like what we're specifying instead of like what are missing in specifications.
Alan.
Yeah, so in answer to Jonathan's question about like what's the next killer app, I can say what the killer application for types is at our end, and why we're interested in it, which is everything that types gives you that isn't error messages. So nobody wants error messages. Red squigglies under your code are just annoying. But my goodness, and if you can give developers productivity tools for things like, we'll show you the API documentation when you hover over an expression, or we'll give you autocomplete, right? People really care about those. And my goodness, those are so much easier to implement if you've got a type system under the hood. And this is not exactly news. IntelliSense has been around for a long time. Most IDEs these days will give you type-based things like type-based refactoring. But I think that side of type systems is one that is rather underrepresented in the academic literature. The academic literature focuses so hugely on type safety that I think a rebalancing of the what is important about a type system, I think that's called for.
I want to continue on that comment about like no one really wants error messages and then type systems. And it surprises me how much people put up with when my undergrads put up with Rust because I told them you are doing your assignments in Rust, but other people do it on their own. And if you had told me that people would do that 5, 8 years ago, I would be like, really? And here we are.
We did a interview study and published a paper at SUPS last year on folks that decided to start using Rust, because I'm baffled too. And so we interviewed 16 people who work on Rust in their companies, and then we did a survey of like 130 people afterwards. And we asked the question about, what do you like about Rust? And we asked about the type error messages. Now, in an academic setting, you could assume that the type error messages suck, because at every conference there's at least one paper about how to make better error messages. but 99% of the people surveyed loved the type error messages in Rust. They didn't hate them. They absolutely adored them. And when we talked about, when I hear everyone say, "Well, I'm sure Rust succeeded for this reason," I question that. All of your reasons seem like good reasons. I think it's the error messages. I think that the Rust tooling was so good. It really was designed to bring somebody who knew nothing to somebody who could learn how to program in Rust, with links to the documentation, with an example of how you could fix it. They really just went all out in going with error messages. So, anyway, yeah, I agree.
Learn from Elm.
Is that right?
I'm hesitating yes.
But Elm was known for.
Elm is absolutely known for going absolutely all out on error messages, and it's also typeset. Sorry, Nate.
No one is listening now, so actually this is sort of proving the point that.
So, if Rust was twice as slow as Java, will anyone use it? If the answer is no, then they're using it because it's fast.
There's more than there's more than just latency.
So no, I agree.
There's also like 99 percentile latency unit garbage collector clauses. If all they cared about was memory safety, is they could use Java, they could use OCaml, they could use Haskell. But the no garbage collection, that's also a huge thing.
If all they care about was speed, they could use C.
That's not all they care about.
Right.
Sure. They want both.
Yeah, no, those are all good points. I think Michael, what you got with your last comment was really just, I think that's sort of what I was trying to access with my original comment up there, which is like, I think a lot of the theories of formal reasoning we've developed are really good, they're really solid, but what they're missing, because a lot of the times it's not publishable, is like the sort of Rust tier of industrial strength error messages, and industrial strength just okay, so if something goes wrong, they have documentation on it, they will guide you step by step through every part of fixing it, and getting the maximum amount of productivity through prototype system. And I think that's really something that's sort of I think outside of the HDIPL community, it's not very widely accepted that this might be the case.
I guess I just wanted to reiterate on some encouragement to try and see if we can do better in terms of error messages in tooling that we can provide. And I have a little bit of a example for I'm working on a deductive verification tool for Rust, and we have inherited some of the nice tooling that the Rust language provides for error reporting. And the experience I've had presenting the tool is with good error messages that say post-conditional violation with just a nice squiggly line around the right place and a snippet of the code and some suggestion on what to do about it. Has been just do demos of the tool and he talks about it, because that immediately gets attention, because people are not used to seeing that kind of feedback. And we've seen people kind of then come back and say, can we use this, because that looks like every other tool that we use otherwise, or at least similar ones. And just kind of in general, I think that's a great run. It's expensive, but I think it's
So I'd like to ask a question about, when you say specification languages, can we be more specific? What is the design space of specification languages? So let's be specific of what do we mean by specification languages, and then let's be a little bit more general about what is the design space of specification languages. So we have a protobuf style data modeling language that we use, and one of the key things about it is that you can specify annotations that are in a separate syntax, that are type safe, that conform to some data type you've already written. So it's a very, very weak typing language, but it seems to be just enough. And I think it fits into the bucket of specification languages, because anything you can't specify in the types, which is not very much, some type of product types, and that's it. You can always put into a structured comment an annotation that you can write a processor for later. So you're deferring, you're making a clean separation between what I know the compiler can currently do for me and what I think I could implement in an interpreter later. Yeah.
Okay, so my opinion is that a specification language, or I should say, a specification is just a simpler rendition of your implementation. So we heard in one of the earlier talks, model-based testing. I guess this was Harry's talk on property-based testing. And that's sometimes what people will do is they'll write a model for their system, and then they'll basically do differential testing between the model and the other system. And why is that useful? It's especially useful when the model is like 500 lines of code and your system is 10,000 lines of code. Because you can look at the model, you can digest it, believe it's correct, and then you can confirm that the two things match each other. So I would say a specification language is any language in which you can write a small model that somebody can understand it. So it could be tests, it could be pictures, it could be types, it could be...
Are you saying that that model is executable or
It is
not executable?
No, it is executable.
Okay, so-
In their case, it doesn't have to be.
Yeah.
I'm just saying it has to be simpler. Because the point of a specification is to be independently understood, that a human can read it and go, yeah, that's what I want. If it's executable, that can help the human interact with it and decide that that's what they want. But it needs to be simpler than the implementation or you haven't gained anything.
So one of the talks earlier, SLE4 is 100,000 lines of implementation and 1 million lines of specification.
Right.
Is that simpler?
I think that there was 1 million lines of
That's really
Well, I just said it was 1 million lines of proof. Sorry, it was Cell4 is 10,000 lines of code, 1 million lines of not specification of proof. The specification is hopefully a lot smaller than 1 million lines. It's the proof parts that are so big.
Yeah, I believe that's good.
An interesting way that we could empirically prove the value of those specification language and making the proof and checking, with repetition would be to compare it with just writing the same code in 2 different languages and then just, run and see if they behave the same and see how many bugs you found. So you could have like a test where you first write your application in a certain language, and then one team write specification, and proofs and see how much time it takes. And then another team just rewrite the same program in another language, and if they have still time in yet another language, and if they have still time in yet another language, and then you can see if by cross-testing, random input on many independent implementation that have used the same amount of human hours as doing the implementation plus the verification, what of the two really capture better the original human intention so that you capture that there can be debug in implementation too. That looked like an empirical way that someone could organize an exercise and check which team get the most reliable software using the same amount of hours.
Michael wanted to say something.
Yeah, thanks. So I'm wondering if there's something to be said about the relationship between the specification language and the implementation language, right? So we've talked about how the specification should be simpler, but I wonder if there's something to be said about, like the typical thing is they're both kind of functional or both kind of declarative, right? But, you could also imagine, right, as is, the case for certain of these projects, right, an imperative implementation and a functional specification or a declarative kind of specification. And so not only is it potentially simpler, but also it's phrased differently, right? So, there used to be a myth that if you had multiple teams implement the same project, then you get different bugs. And of course, it turns out not to be true because the complexities are the same. On the other hand, if people use different tools, maybe even if it's the same person, maybe you get more reliability, right? Because maybe the mistakes that you make when writing the specification, if you write the specification in a very different style than the implementation, maybe those are actually very different than the mistakes you make when you write the implementation. Seems like an underexplored area.
To return to a thing that we kind of mentioned before, like what is there beyond types? And some of us have been working on different type state things for 20 years or not working on it or whatever. So that's another thing that I think is beyond types and take more of the specifications.
Michael, to your point, Daphne is essentially what you're talking about. So in Daphne, you write your specifications as pure functions, you write your implementations as imperative code, and then you intermix these two things. I was going to say another example for your test is you don't even have to use different languages for your implementation. So when I was a software engineer before I went to grad school, I read this book called Writing Solid Code by Microsoft, and they talked about, in addition to using assertions, that was the first place I ever saw that, they talked about writing the implementation twice, where you would write the fancy one and you'd write the simple one. So they talked about in Excel, they have this fancy, you know, propagation. When you make an update to a cell, you have to propagate to all the other cells, and they want to do caching and, you know, dynamic programming and stuff like this. But they also have just a dumb way where you recompute them all. And they would just always cross-check one against the other, simple algorithm versus another one. You can think of the simple algorithm in the same language as the specification, and the more complicated one is your implementation.
That's exactly how I teach my students to debug. I say like the simplest way, you know, is that you don't do optimization code first. You start with a simple implementation, and then you write the complex one, and you cross-validate. I propose to different languages in order to try to avoid the thing that, you know, was said there, where the same person or even different person but humans, you will do the same mistake because they have the same complexities in some sense. By changing language paradigm, by doing in a functional object-oriented imperative, maybe there is some noise, you know, and so we change the place where there is the bug.
So it reminds me in the art world, there's a notion of maquettes. There's a notion that you think and you experiment in a different, explicitly in a different medium from the final product medium. It's also pretty hard to kind of think and play in Marvel. But I would argue that it's probably reasonably hard and difficult to think and play in my case in Rust rather than in something else. To start off with. Yeah, it's just the look at that. I'd love if we could concretely come out with that. This is a list of specification languages that we have, and this is the properties that you know would. I'm reminded of a paper that I read from when I was an undergrad from Treaty of Orlando, which came up with a definition of OO. It then took a little while later to kind of flesh it out, but you know, I still think we would have disagreements about what fits in and does not fit into what a specification language is, and I think that discussion would be interesting and informative.
Yeah, what do you say?
I don't want to speak.
I think Alcides said his hand.
Oh, yeah. Alcides?
Yeah, sorry, it was the volume was a bit low on your side. Yeah, I just wanted to add that we worked with a NASA and as a contractor, and they asked 3 companies to build the software and 2 others to write tests for the specification. But the specification was always the same, right? So they didn't gain that much by hiring 2 different companies to write the tests because they would both enforce the same specification. But if there was a problem in the specification, all 5 contracts would be very costly. So even in critical software, there's like a ratio there where how much effort should be spent on the specification versus the software itself. And this is to bridge with maybe the question that Michael asked a while ago in the chat about is there a testing approach to help people write specifications, right? So I think with AI and synthesis, you could actually take the specification, synthesize an implementation, and see how much it passes the test suite. But as said before, this only works if the specification and the test suite are written by different people, right? So they don't have the same biases. And I agree that you could see just test suites as a different language than the other specification language. They're both languages just with different natures, as has been discussed.
So one, you know, when you think about specification, there's a cost to doing specification, right? There's a cost, but however you do it. formal specification, alternative implementations. And it seems like, in our community, we assign infinite cost to there being any correctness issue and zero cost to specifying the correctness condition. But of course, when you talk to people in industry, that is not at all how they think. Right? They think, in dollars, how many dollars is it going to take to spend this amount of engineering effort on writing specifications? And there don't seem to be tools that help people do cost-benefit analyses, like where should specifications be written? What would the cost be? What is the potential savings, right? If it's really branchy code where the wrong outcome is going to cost you a lot of money, that's the place you should put in that engineering effort. We all defer that to the organizational aspects of software development, but maybe tools could help.
The thing is, industry will never trust a developer, but an artificial intelligence then tell them, oh, this is it, we'll be trusted.
I think that's a really good point. The point I was going to make is, in terms of the job of a specification language, is it also to communicate requirements, or is that a separate task that then one derives the spec from?
Good question, though.
We have a live interactive doc that Google Doc or something that you want to jump into.
It would be a nice idea, but now we're 6 minutes there.
I think we should start it so that we can continue the conversation up.
I would love that.
So I just want to tie together a few ideas, including the ones just brought up. But kind of before we were talking about how Rust might in part be successful because of its great error messages, and I think this kind of goes to show that when we're talking about verification, we're usually talking about the cases where we want to ensure the correctness of the program, and we don't really consider what do we do if the program's incorrect? We just reject it, right? So maybe there is some value in tools that kind of guide incorrect programs towards correct programs, and kind of some ideas that come to mind like incorrectness knowledge logic, or kind of related to Cyrus's work, assigning semantics to partial programs or partial specifications. And I think maybe that could be a good direction and lead to better adoption than purely focusing on correct programs.
Yeah, it's a very Mark Meinhardt thing.
Michael has something to say. I see you doing that.
Yeah, so that's a really interesting point. So Mike and I worked on this observational study of Rust developers, which we're in the process of writing up. And one of the things that we saw is that it can be really hard for programmers, especially novices in Rust, to figure out whether their change to their program in response to a compiler error is actually making progress, right? So they've got a program, it doesn't compile, they make a change, it still doesn't compile. Do they make forward progress or backward progress, or is their change orthogonal to the problem? Right? It's really not clear. And I think that the stricter the type system is, the sparser the space of passing programs, right? And so if you can run the program, that might give you some feedback about what kind of bug it is. Even if you know that there's a bug, maybe you want to run it and see what the output is and judge from the output what the problem was, as opposed to, I'm sorry, there's some error, and I won't give you any output until you fix this error.
Right, and I guess in practice, test-based development is really popular in part because, you have these 20 tests, and if you pass 10 of them, make a change, now you pass 16 of them, that's visible progress.
Sorry, were you?
I guess I'd follow-up comment on this, which is, as somebody who's written a lot of Rust and some concurrent and some non-concurrent Rust, I think the comment you'll have is probably applies to non-concurrent code, so where the ability to run and get feedback of typing correct code is valuable to debug it. I'm more concerned on where the subtle bugs that show up only sometimes, so it's specifically concurrent code, but then applies to other areas as well, where I really want Rust to prevent me from writing some code that will explode at runtime 3 months from now in production. And so I guess maybe there's a distinction between the kinds of programs where this approach applies better than others, I suppose.
On a slightly different topic, I noticed there was a question asked in the chat somewhere. Is there a testing approach to help specification authors assess how complete their specs are? I promise this is not my thing, but there was a student research poster or something about mutation testing, where you sort of just mess up the program source and see if like the spec still passed, and if so, you know, that spec is probably not complete enough, right? So that was kind of a cool approach for I guess it was Michael who asked that question. Something to look at.
One thought that I had during the discussion was it's a natural idea to infer specifications. So there's this work that goes back a long time, DICON, plus there's many approaches since, where you take code, you run it a bunch of times, you infer specifications from the code, and you say, also now I have a specification. Except I think the problem is with this redundancy issue is we want them to be different. We want someone to deliberately decide what their specification is and use that as the truth and then compare it against the implementation. And if all the information is derived from the same source, the implementation and the benefit of the specification is not there. In as much as that it's complete. Sometimes you can accidentally get benefit because the kind of properties that you infer from your spec inference are different or they're phrased a different way and they're heuristic, and maybe that sheds some light to you when you look at them. Oh, that's not what I meant. So the tooling can help you, the human, ultimately arrive at the specification. I was thinking, sorry, wait, one last thing, that one way that automation could be awesome for specifications is to go the other way. Instead of basically deriving your specification from text, that is running your code and then making a general spec from it, go the other way. Write your code in your spec and then generate a pile of text from your spec. Because if you have a full specification, essentially that's like property-based testing. You can imagine synthesizing a ton of text from that. And then people can look at the tests. Maybe they can't make sense of that specification, but they can look at the individual examples and go, yeah, those examples look right. Those look like the right instances for me. And then that gives you more confidence your specification is correct. And of course, you can use it to test your implementation.
Having kind of looked at the DICON stuff recently, like it's kind of swept under the rug, but the DICON actually kind of uses tests a lot, right? It doesn't, the specs don't actually come from the code themselves. The specs come from the interaction of the tests, which he doesn't really ever talk about at the code. And then the last thing you said, yeah, then you're like, it's property-based testing, and yeah, you have this abstract spec, which I think is hard for people to actually deal with, and then the tests make things very concrete. And that's one way of thinking about maybe the easy case, but then the edge case is what people don't think about. So maybe property-based testing can actually make the edge case visible. So I guess you have a URL now in the chat, but those of us are here. Can't really do anything with the URL.
Yeah, I'm trying. I put it in shared drive. I might move it to somewhere else.
Try setting access to anyone with the URL.
Yeah.
Because I put it in shared drive, I'm going to put it not in shared drive.
Got it. Okay.
But it's also on this chat that we don't necessarily look at, right?
We can share it up.
So kind of my reaction to the idea of starting with tests is why not just go the whole 9 yards there and just consider the tests as examples and perform some kind of generalization and program synthesis, which already exists, to take a few examples, generate a specification, and then generate code for that specification. And I guess kind of where I'm going with that is it might be nice to see a little bit more correct construction synthesis at HATRA.
Yeah, that's an interesting idea. And I guess just to sort of summarize the discussion so far, I think one reason it's hard to come up with like a definition of what is a specification language is because the problem with specification is sort of very, very fundamentally a human one, even more so than programming itself, because specification is like, okay, like what is the purpose? It's basically talking about what is the purpose of this program, what do you as the human want it to do. And I think in that sense, a lot of the like maybe a lot of the current work on specification languages is sort of taking too narrow of a view of it, right? So like if you have to, it's reasonable to sort of extend the definition of specification languages to include like, okay, like if I make a UML diagram of my program, maybe there's some interesting properties that could be had and sort of making sure that like architectural constraints are being followed or something like that. So maybe like broadening the horizons of what it means to be a specification language is worthwhile, and attempting to define it very narrowly is maybe not what you want to do. Maybe it's exactly the opposite.
All right. We have had a really interesting conversation, gone a lot of different places, but I see it's 3:02, so we should probably wrap things up. Here, I'll say this. But thanks everyone for coming. Thanks for the great conversation. I think we do not have the next session, so find people to talk to or other interesting things to go to. And yeah, I hope we'll organize something similar next year. Do you want to add anything, Michael?
Yeah, thank you all so much for coming and for submitting all your wonderful papers, and to Jonathan for facilitating in the room today, and to everyone on the PC for reviewing all the papers and giving all that great feedback. It's been a really interesting workshop, and I look forward to seeing everybody's submissions next year.
Send it to me and I will do it.
That's good. I'm sure I can probably but you ask if you're
Yeah, hold on. Oh, yeah, I remember. So basically I think there was kind of counting where you're saying, you know, you better have lattice, but in practice, I think there's like edge relations on a graph. So I was wondering if you're looking at using any sort of universal construction to either take the lattice and generate minimal constraints from that lattice, or vice versa, take like a programmer specified constraint and then